Hi, I'm so sorry. I got kicked out. I'm finally back. Just 1 second, please. Okay. All right. Sorry, we got disconnected. As I was saying, that for translational motion, we care about the center of the mass. So what this really asking is, what kind of motion is the center of mass is following? I wanted to remind you that Newton's second law, F equals ma. Okay, still always apply to the center of the mass. Remember, no matter how complicated rotation that this object might follow. Remember, we're doing the toss of the object and we highlight the center of the mass. That's the demo we see. The center of the mass is still following the parabolic motion. So Newton's second law still applies. So you can do the same thing here, F equals ma. The force is the same. So apply to the same mass, then the center of the mass acceleration is the same, which means how fast they're moving in the translational direction should be the same. So the answer to this question is that they will arrive at the same time to the finish line, okay? Because that is the center of the mass we're following. Now the next question is asking, instead of the which one finished first, is asking after 5 seconds, which one have a greater center of the mass speed. So velocity of the center of the mass will be acceleration of the center of mass times time. Okay, so you had just said the acceleration is the same because it's governed by the same force according to Newton's second law. So which means they should also have the same speed, right? We answered they will have the same speed at different time at the same time. So which means they arrive at the finish line first. So this one, the answer is also C. They have the same center of mass speed. They arrive at the finish line first. The next one has to do with the more nuanced rotation. So 5 seconds later, which part has greater rotational kinetic energy? Kinetic energy for rotation is 1/2 I omega squared. Okay, I is inertia, rotational inertia, and omega is the angular velocity. So this one I will have you vote, okay? I'll give you a minute to discuss, and then after you come back, you could vote on this one. Omega, the angular velocity, just a reminder, is angular acceleration times time. Okay? So if you need that information. All right, let's go for 10 more seconds. Any last minute vote? Okay, let's take a look at this together. I'm going to go ahead and close it. All right, so looks like you, majority of you agreed that the puck one will have a greater rotational energy, okay? But actually almost half will choose puck two, or maybe they have the same for both of them. Okay, so to compare this rotational kinetic energy is 1/2 I omega squared. What about their I? What about the rotational inertia between these two? 1 and 2, do one of them have a bigger I than the other, or do they have the same rotational inertia? What do you think?
I think we said that the rotational inertia for an axis through the center of mass is always smaller.
Mm-hmm. And they are rotating through which axis they're rotating?
2 is through the center.
Goes through the center, very good. Yes. So 1 and 2 will have the same rotational inertia. They are identical and they're both rotating through relative to its own center. So they have the same I. Very good. I'm glad that you mentioned to which axis, because you can have two identical objects, but if one of them are rotating to a different axis, then they may have a different I. So I is the same. So really we're comparing omega between them. Omega is alpha times delta t. So all t is the same after 5 seconds. So really we're comparing which one have a bigger angular acceleration. But again, we come down to which one, what generates angular acceleration? Torque, right? Torque generates angular accelerations. Torque equals I alpha. So I is the same. Again, now we're comparing which one has a bigger torque applied to them. So which one do you think? 1 or 2 has a bigger torque applied to them?
One is more torque because it's being pulled at a further distance away from the center.
Very good. One has a bigger level R, a bigger R, so it's a bigger torque. So torque 1 is bigger than torque 2, then alpha 1 means alpha 1 is bigger than alpha 2, which means omega 1 is bigger than omega 2, and eventually you get kinetic energy 1 is bigger than kinetic energy 2. So A is correct. So here is a very interesting question, is that if you apply the same force to both of them, one actually have pick up more speed, will start rotating faster. So where does that energy come from? Where does that energy come from? You know that if you have, so one certainly has more energy, right? They're moving the same translationally, but one at the same time, one spinning faster. And where does that energy come from? It has to come from somewhere. Where do you think the energy comes from? What causes energy input?
A force?
A force. Force has to do
Work?
to do work. So in this case, it must be one has more work done to it. Does that make sense? You're pulling them with the same force. How come one has more work done on it? So work is force times displacement. In this case, if we know the force is the same, then if I also concluded one has more work, which means one must have more displacement. But didn't we just say that 1 and 2 are all across the same distance? So is this translational distance the displacement we're looking for work, or is it something else?
There was the added displacement of rotational energy.
Displacement of rotational energy. Can you say more about that? So if I want to look,
There was more displacement because the portions of the disk were spinning as well.
very good. The one will unravel itself much faster. So if you're looking at the string will unravel yourself much faster. So yes, you may be using the same force, but to exert the same force on both, you will find yourself have to reach out your arms way further for one because your string is already unraveled. So you have to like let it go further. That's your arm. So that distance, your displacement is how much the string unravels, not really the distance it traveled through the center of the mass. It's how far away your arm pulling that way. So because one unravels really fast, you have to pull your string kind of further back. Therefore, you're doing more work, even with the same force. And you're putting that, translated that work into the kinetic energy of the rotation for part one. Okay, so part one is correct for this problem. Okay, now we are ready to solve some problems using conservation of the energy approach for rolling without slipping. As we said previously, you have to consider two different energy terms. One is the translational motion. V is the translational velocity through the center of the mass. The second one is the rotation relative to the center of the mass, right? So the object is spinning and going forward at the same time. When this is rolling without slipping, the velocity of the center of mass is r radius times omega. We derived this previously already, right? Because if it's slipping, then it doesn't slip in one revolution, the circumference of the ball is exactly how far you have traveled forward. Now, notice this really requires static friction to prevent slipping. So you must have static friction to generate this rotation. If you don't have static friction, then the object will just slide. It cannot start rolling. You definitely need static friction. Okay. All right, so the first question we have, example we have, is an example that's very similar to the one we did, unraveling the string, except pulling in this way. Now you let it drop down this way of a yo-yo. Okay, so we have a mass M and R for the yo-yo. We start from the rest and it's dropped. So you can see simply it unravels itself as it dropped. What is the center of the mass velocity after falling down a height h? So we want to know the center of the mass velocity. Okay, so we're going to use conservation of energy approach to this. The only tweak we are making right now is to add an extra energy terms that is a rotational kinetic energy on top of 1/2 mv squared. Okay, so let's see how we do this together. We can use conservation of energy approach. And in this case, we will choose the yo-yo and the earth as our system. Okay. Because I want to be able to talk about the gravitational potential energy. So at the very beginning, it's unravel and drop for a height h, right? So at the beginning, then you are at a height h above wherever you set your reference. So your potential energy for the system is energy h to begin with. And after it dropped to the lower location and it has no potential energy, your system has kinetic energy. Okay, so the kinetic energy is 1/2 mv squared plus 1/2 I omega squared, right? Two terms, because it's not just dropping, it's also rotating. So we add those two terms together. And this is rolling without slipping. Apparently, how much you're rolling is the length of the thread. The length of the thread is also how much you're falling in the translational direction, right? So this is rolling without slipping, which means the velocity center of the mass and the spinning speed, they are related by r. So that's it. Okay, so just to go back here, we said use this approach and we use this system, yo-yo and earth. Sorry, E final, E initial, E input, and E output. Okay, E final is at the lowest possible point would be kinetic energy O only kinetic energy, so velocity times 1/2 I omega. Okay, and velocity and omega are related, so I could change my omega to velocity over r. So I'm going to do the substitution here. Omega is v over r. So I'm going to do it here. Initial, you have mgh, which is all potential energy. Don't think about friction. You don't have to think about the drag of the air. And you don't have any inputs either. So no input and output. So let's put it into our conservation of the energy equation, which means this is going to equal to that. Okay, 1/2 mv squared plus 1/2 for the yo-yo. It usually in the shape of a disc. So we know that for a disk, we can use 1/2 mr squared for the rotational inertia. Okay, I'm going to replace I with that. And again, over r squared, the center of mass squared. Okay, so from this term is equal to mass GH. So you could do some quick cancellation. For example, you can cancel your m. I can cancel my term r, and you can find your velocity of the center of the mass, right? Which is calculated here. Is square root of 4/3 GH. Okay, you can see the final answer doesn't really depend on the mass of the yo-yo. It's 4/3 times GH, square root of that. So you can see this is something we are familiar with. Conservation of energy, you already know it, but we simply add in extra terms in the problem and use the condition for rolling without slipping. Okay, we have one more example. Okay, so this one, I'm gonna let you have a little bit more time to try to do yourself. This, recall, we have a rolling for a race between different objects, right? We compared a hoop and disc. You could compare a disc and a sphere, or you can compare a hoop and a sphere. So there are two objects in this problem, a hoop and a disc. They have the same mass, the same radius, and they start rolling without slipping from the same height of the ramp. Okay, so which one reached the bottom first? You already know which one wins because of the previous clicker question and the demo we saw. But let's actually try to calculate which one has a bigger velocity center of the mass, right? Because the one with the bigger velocity is the one who's going to go down first. So first of all, I want you to think about, okay, actually we can solve this problem two ways. We are going to start the conservation of energy approach first. That's more straightforward. This problem can also be solved using dynamics, where you draw a force diagram, and kinematics. So I'm going to show the other approach later. But let's do the conservation of energy approach first. Okay, so I want you to think about, okay, what is your system? It's your choice of your system. And what is your energy of this system at the beginning and initial moment and the final moment. So I want you to spend a little bit of time to think about these terms before we do it together, okay? Think about what is your system, what is your final energy of the system at the final moment, what is your initial energy at the initial moment, what's input and output. So I'll give you 1 minute to think about it. Okay, let's look at this together. So for simplicity of calling the object, we're just gonna say the object, right? Because the difference between a hoop and disk is they have different eye. So we're gonna call this object, and then we will make a distinction in the calculation later, which eye are we going to use. But now we just consider a rolling object. So what is your choice of your system? Anybody would like to share their thoughts with us? What system do you want to use? System of the RAM? What system should we choose? Guys, this is not a trick question. I hope that at this point, we should be very clear in the application of conservation of energy. Okay, thank you for the chat. Object and the earth, very good. Object relative to the earth. Yes, very good. So we're going to choose the object we're interested in because here we wanted the velocity of the object. Obviously, we should include the object. But you probably wanted to be able to talk about potential energy, which means you should have included Earth in your system. Excellent. All right. Because if you include the Earth in your system, then gravitational force between the object and the Earth is no longer an external force. You don't have to think about the work done by this force, okay? So initial moment, I assume initially is at a height h at the top of the ramp, finally is at the bottom of the ramp. So final energy, when the object is at the bottom of the ramp, what kind of energy the system has? What kind of energy? Kinetic, very good, kinetic energy. And the kinetic has two parts. One is the object as a whole is going down, translational part. So I'm gonna say M, capital M, V center of the mass squared, and the V center of mass is the one you're trying to calculate. The object is also rotating relative to its own center of the mass, so that's 1/2 I omega squared. Okay. And omega is related to V by R, so if you want to do the substitution here, you could. 1/2 I omega is R V squared over R squared. Okay. Because it's rolling without slipping. So this condition gives us V is equal to omega R. Okay, fine. Initial energy when the system is at height h above the ramp. So it's releasing from start. So we have potential energy, and that's mgh. Is no energy input. And also I wanted to make sure that to talk about our energy output. What do you think about our energy output? Do we have energy output in this case? Oftentimes when we do have an energy output is when we have friction, kinetic friction. We have kinetic friction here. Implicitly, it says rolling without slipping. So it says we have static friction. We certainly need static friction, so just static friction. Very good, and it's no slipping, right? Kinetic means like you need to slip, you have to rub through the surface. So no slipping, no kinetic friction. And it's really just the static friction because we know without that, it's not going to roll. So do you think static friction would do work? And would that work be counted into the energy output? Does this static friction do work? Do you think static friction doing work in this case? So for something to do work, you need to apply the force over a certain amount of displacement. And very good, thank you, Gabrielle. The answer is no. The reason is your contact point between your static friction and your surface is really changing all the time, right? Think about your rolling. You're moving to a different contact point, you know, in different instants every second. You're moving away from the original contact point. So there's never a displacement along with the direction of the force, okay? So 0, and we're going to make a note saying static friction does not do work, but it does contribute to rolling. In the, we will talk about how to view that using a dynamics approach later. But here, an energy approach, all we need to know is no energy output. So you just need to set these two terms to be equal. Right, setting these two terms to be equal, you got this result. I have factored out the velocity center of the mass. And I'm keeping I as it is because your final answer will depend on the ratio between I and M. So I'm not going to plug in the specific I. Different objects will have a different I. That's why I'm keeping the rotational inertia as just I, because I want a more general expression so I can use it for different objects. So you have solved the velocity of the center of the mass, which is simplified into this relationship. Okay, so you can see different objects will have different I. If you're looking at the hoop, you will plug in I is mr squared into this equation. Okay, if you do that, you get velocity for the hoop is going to be 2gh over 1 plus I is mr squared over mr squared, you get 1. So you get square root of gh. Okay, if you're looking at the disk, the I is 1/2 mgh. So this becomes 1/2. Okay, so get 2, 3 over 2. So you get 4/3 gh. Okay. So the disk will come down first because the disk has a bigger center of the mass speed. Okay. All right, so that is the second example we have. To expand on the result a little bit more, we are giving you now a disk with 2 different disks, the same shape, but they all have different masses and radiuses. Okay, one have a smaller mass and a smaller radius, one has a bigger mass and a bigger radius. Which one win the race? Okay, now recall we have already derived a generic formula for racing objects that is 2gh over 1 plus I over mr squared. Okay, so using that expression, would you be able to answer this question? I'll give you 1 minute in the breakout rooms, okay? So direct application of the equation we just derived. Okay, let's go for 10 more seconds, okay? 10 more seconds. All right, any last minute votes? If not, I'll go ahead and close this. All right, so this is our result. Seems like the majority of you think it depends on M and R, or probably they may tie as B suggests. You can see that M and R, the mass and radius does enter into the equation, right? However, there is another quantity also has M and R in it. That is the rotational inertia. For the disk, okay, for a disk, the general is 1/2 mr squared. That is the I for rotational inertia. I for disk is 1/2 mr squared. So if I'm looking at the smaller disk, I will plug in 1/2 mr squared for the small disk divided by mr squared for the small disk, right? So m cancel, r cancels. And I'm doing the same thing for the bigger disk, that I will do the same thing, 1/2 capital M capital R squared over capital M capital R squared. And you can see again, the mass cancels, the radius cancels. It turned out the mass and radius doesn't really matter. The matter is the rotational inertia I over the mr squared. So as long as you have the same type of an object, they will rolling down with the same speed, right? Isn't that interesting? That's suggested by this calculation. Okay, so they both have the same center of the mass speed, so they will have a tie if they would race down from the same height. Okay, so that's very important. That's why we keep this as an I here, so we can see it's this ratio that matters. Okay, so this ratio matters, not the individual I and the individual radius, individual mass or the individual radius R. So B is the correct answer. Okay, so the above method I'm showing using conservation of energy. We can solve the same problem by using a combination of dynamics, force, drawing free body diagram, and kinematics. So let's first of all, let's draw the free body diagram of the hoop. Okay, I'll give you a minute. On your notes, you can go ahead and try to draw free body diagram for the hoop. Or it could be a disk, but I'm just going to use a hoop as an example to do the calculation. I'm trying to solve this problem using a different approach. So drawing all the forces that's acting on the hoop right now, okay? All the forces acting on the hoop right now. So let's talk about the forces one by one. Anybody would tell us one force to start out with. Name one of the forces acting on the hoop. Gravity, mg, very good, thank you. Okay. Force of gravity. Okay, and as we see that someone said normal force, so gravity pointing down, normal force is perpendicular to the ramp. That we know already, very good. Anything else? I see F of N as normal force. Yes, very good. Thank you, Alexander and Eric and Tennis for saying that. Do we have any other forces?
Friction.
Static friction, very good, because it's rolling, and we know that you need static friction in order to roll. So in which direction is your static friction? Pointing up the ramp or down the ramp?
Up the ramp.
Up the ramp like this. And why is that? Why is it not down the ramp?
Because friction opposes the direction of motion.
Okay, and how do we use that to figure out the static friction is up the ramp?
Because we know that the object is rolling down the ramp. So to oppose the downward direction, then we'd have to have the friction pointed up the ramp.
Ah, I see. Yes, so here, the object is rolling down the ramp. And you can see that the direction of the friction should give us a consistent rotation that is rotating down, right? So rolling down, you can see that it's rolling down. This is rolling down, right? So imagine a force applied up in this direction is making this entire rotation to be called it clockwise, which is consistent. If your friction is this way, you can see that would have given you a rotation is rolling up the ramp. Okay, if they were actually rolling up the ramp, then you know which way your static friction is. But rolling down the ramp, right, the friction has to be this way. So you can see that it's pushing the object, giving it a torque, so causing a rotation that is rolling down. Very good. Now we now have all three forces. So what can we do? Instead, we're going to use dynamics approach, which means we're going to use Newton's second law. So Newton's second law is still applied to the center of the mass of the object, right? So we can add up all our forces in two different directions. The x and y direction, I'm going to call this x and this is y. Okay, so my z is x cross y, so my z is out of the page. So I'm going to use a dot to represent it coming out of the page. X and y, z. The y direction is really the component of a gravity cancel out friction, so less interesting, but we were going to focus on the x direction. In the x direction, you have two forces. You have the component of gravity, this component, right? So I decompose my gravity, break it down into x and y component. After I do that, I cross out my force of gravity so that these two forces are already accounted. So this is Fg in the x direction. Okay, if this is theta, and this is theta, okay, which means this is theta. Okay, so the x direction is Fgx times in the positive downward direction minus static friction in the opposite direction. So this is F net equals ma, m times acceleration. Right, so I applied Newton's second law for this motion. Okay, and this is the sine theta component of mg. So mg sine theta is your component static friction. Okay, ma center of mass. All right, so here we applied the dynamics for translational motion. But don't forget, we have Newton's second law for rotation, right? Rotational dynamics. Have another equation coming out of that. So what is the rotational dynamics? What is the Newton's second law, the equivalent of this for rotation? Anybody still remember? So instead of force equals ma, we have what equals what?
Torque equals the moment of inertia times the angular acceleration.
Yes, so torque equals I alpha, very good. So we're gonna use this again because we know that friction is causing this torque, and I can probably relate my alpha to my A. So I'm able to combine all these information together. Okay, so what is the torque generated by the friction? Torque is force times the level arm. So in this case, what is the torque generated by the friction? Friction this way, and let's call this radius r. Torque is r cross f. So in this case, it's going to be static friction times radius r, right? Okay, so that's my torque. Okay, I is, we're using a hoop. So I'm just going to use mr squared because it's a hoop. Now, if you're dealing with different rolling objects, obviously you have different I. Alpha. Alpha is the rotation, angular acceleration. Because we know that v is equal to omega display. So we take the derivative with respect to time. We know that dv dt is acceleration a, center of the mass, which is this quantity, equals r d omega dt. What is d omega dt?
Alpha.
Alpha. So you can see a and alpha are related like this. So I can replace my alpha by a over r. Okay. So what do you got? You got one equation, another equation, and you have two equations, two unknowns. Which are your unknowns? You don't know A, you don't know force of static friction. Now, which means we can solve for them, right? Put it together, we solved it. And the result is the acceleration down the ramp is 1/2 g sine theta. Okay. So now we know the acceleration for the center of the mass. To get the speed is quite simple, right? It's the translational motion we're interested in. So you combine with kinematics. It's something we learned in the very beginning. So it's a constant acceleration down the ramp. Okay, for the center of the mass is constant accelerating down the ramp. So I can use this equation. Initial speed is 0. So I need to know the final velocity for the center of the mass, which is 2a times the length, the entire length of the ramp. Okay, so a final little substitution for the length of the ramp is, if this is h, then the distance traveled along the ramp is going to be h over sine theta, right? Because this is theta. So the hypotenuse of the triangle is h over sine theta. So plug in delta x in here, plug in your a that you just calculated, and you find that the center of the mass velocity is square root of gh. Okay, is that something we got previously? For a hoop, right? This is something we got previously using the conservation of energy approach, square root of gh, right? So we have down this 2 different ways, and we got the same result, which we showed. So conservation of energy approach is much more straightforward, but I think it's very cool to also show we can do the same get the same results using a combination of Newton's second law and kinematics. Newton's second law, you need 2 Newton's second law, the rotation part and also the translational. All right, so that's actually all I'm going to talk about for the rolling object topic. We did the Newton's second law. Now remember our different threads of thoughts. We had kinematics and then Newton's second law, dynamics. We did conservation laws later. That's energy, conservation, momentum conservation. And then we switched to do rotation. For rotation, we do the same thing. We talked about kinematics, quantities, the dynamics for rotation. And the third is also conservation laws for rotation. So which means we start our discussion of conservation of angular momentum for rotation. But before we can talk about the conservation laws for rotation, we have to introduce what is angular momentum. Okay, so this is paving the way for later on. We do conservation laws for rotation. Again, momentum is conserved. We had a conservation of momentum for earlier for collision type of problems. We have another counterpart for if you have rotation, we call it angular momentum instead of linear momentum. You probably already see for we're simply replacing these quantities with the rotational counterpart. So mass becomes rotational inertia I, linear velocity v becomes angular velocity omega. Okay, so angular momentum L is simply I omega. Okay. So for angular momentum is a little bit of nuance because sometimes you have an object that is rotating, you have continuous distribution like a sphere, like a hoop, like a disk. Sometimes you can look at the object as a point particle that could also be rotating, right? We'll use slightly different formulas for the angular momentum, but they're really related. So if you're talking about this equation that we had just use the counterpart for m and v, that is when we are dealing with a continuous distribution, like a ball, like a rod, like a sphere, or like a hoop or disc, that kind of thing. We use I omega. But if you're dealing with a simple point particle, like if you're looking at a satellite going around the Earth, then we define our angular momentum to be r cross p. Okay, so I'm going to draw a little diagram to show what I mean by r cross p. So let's say you have this little point particle is going around in a circle, doing a rotational motion, and r is from the center of the rotation to the direction of the front to the point of the object. So this is your r. Okay, p is linear momentum. Okay, mv. So velocity is this way, right? That's why p is here is mv. So r cross t give us the angular momentum. Okay, you can kind of take a look at the direction of that. So extend r a little bit this way, so you can do your cross product between r cross v, that is upward. So you can see this kind of counterclockwise rotation is pointing to an angular momentum that's upward. Okay, which makes sense because if you are rotating this way, your angular velocity is omega, which is upward by the right hand rule. So L is in the same direction as your omega, which is upward. Okay. It also, you can see L equals RP can be translated back and forth between I omega, because just for a point particle, R in this case is little r cross P, right? R is R, capital radius in this case. P is MV. And at this point, they have a 90-degree angle. So the cross product between two vectors is A times B times sine theta. So sine 90 is 1. So this reduced into RMV. And you can see my V is omega R, right? So that's the different, that's the relation between V and omega. So I can put m r squared together and omega together. You can see for a point particle, the rotational inertia is mr squared, that is I, and times alpha. So you can see these two are actually give you the same results. It's just when you're dealing with point particles, we tend to use this velocity, this definition, and we're doing with a rigid body, a continuous distribution, we use a different expression. Okay. So to quickly try to practice the idea of angular momentum, here I'm giving you a question with 3 different spinning objects. They are all identical with the same rotational inertia. They're spinning with the same omega. Okay, they're all spinning up right now. So the total angular momentum is 3I omega. Each one of them is I omega. Let's flip one of them upside down. So, and then what is the new total angular momentum in this case, if I flip that upside down? I'm going to let you go ahead and you can have a discussion for a minute or two, and then after you come back, you can vote. Okay. All right, let's go for 10 more seconds. If you haven't voted already, please do so. Okay, any last minute votes? All right, I'm gonna go ahead and close it. Look at our results, quite split between A, B, and C. So how do we figure it out? If we simply flip one upside down. Okay, so angular momentum is it a scalar or is it a vector?
It's a vector.
The vector, the direction L is decided by omega, so the same direction, okay? All right, so if one of them is I omega, let's say we flip this one. So before we flip it, we say this is I omega. So once we flip upside down, what is the new angular momentum of this wheel? So this
Negative
is
I omega.
yeah, it's going to be spinning up to going down. So if you spin counterclockwise, first we say your velocity is decided by the right-hand rule is up. Now if you're spinning the other way, then it's down. So I'm gonna cite that's negative I omega, right? You represent this vector using a negative sign showing the direction has flipped. So what you had is the three of them together is I omega plus negative I omega. Okay, and then what do you get from that? So IL total is going to be what? I omega. Okay, so just one I omega. The 4 is all three in the same direction. 3 I omega. It flipped one of them, now it becomes I omega. So C is the correct answer. Okay, C is correct. Okay, so how do we get the conservation of angular momentum from this? Again, we follow the same analogy when we do this derivation. We already did the analogy to figure out what is angular momentum, right? Is I alpha, L is I omega, and corresponding to mv for the linear case. The Newton's second law, remember F equals ma, there's another way to write it. We have talked about this before, is F equals dp over dt. Remember how that came about? Is acceleration is dv over dt, right? And usually when we are dealing with mass that's constant, that's not changing, so you can take m into your dv derivative, so it becomes dmv over dt. mv is momentum, right? So it becomes dp over dt. F equals dp over dt is Newton's second law. And now what does it become? Again, F becomes torque, force becomes torque, T is still T, time is still time. Linear momentum becomes angular momentum. So it's L, the L over dt. Now we have a new Newton's second law for rotation is, this is equivalent to I alpha, okay? This is equivalent to that because you can see alpha is the omega dt, and if you put I together with omega, and I omega is the L dt, right? So it's the same. So torque is the L over dt. The change in your, the rate of change of your angular momentum is the torque. Just like the rate of change in your momentum, linear momentum is your force. So we did exactly the same mapping as we did before. So recall previously, if there's no external forces, if F net equals 0, then dp equals dt is 0. Meaning that when there's no external force acting on the system's momentum remain constant, right? So if it's constant, meaning if you look at the momentum at the beginning, if you look at the momentum at the final moment, it does not change, it's the same. So P final is equal to P initial. So it's a constant momentum. That's conservation of momentum, right? When there's no external force. When there is, then you have to think about the impulse acting on the system. But when there's no force, it's really just PF equals PI. So likewise, in this case, if there is no external torque, which means the change of angular momentum over time is 0. the L over dt is 0. Okay, so from that equation, can you write what the conservation of angular momentum looks like? Conservation of angular momentum. What does that look like? Anybody?
L final minus L initial equals 0.
Yes, exactly. L final minus L initial equals 0. There is no change in your angular momentum. Very good. So we're going to be able to use this equation to solve a lot of problems. Okay, just like we did with this equation. So for angular rotational case, we have a conservation of angular momentum. Okay. Okay. So here is a checkpoint question. We did. It's really it's an idea of if there is no external torque, the angular momentum of the system should remain constant. So let's look at this together. Okay. So we have a rotating disc, and from the top view is rotating in the counterclockwise direction with angular velocity omega. But you toss a heavy block onto the disc along the direction. So along the center through this line. So from the side view, it looks like this. Friction acts between the disc and the block so that eventually the block is at rest on the disc and rotate with it. What is the magnitude of final angular momentum of the disc block system compared with the original angular momentum L? Okay. So, so here, first of all, for any kind of these problems, we have to think about our system. And we need to think about the initial and the final moments. And we have to think about the angular, here it's curious about angular momentum. So angular momentum initial and angular momentum final. So what would be the choice of our system? It's already told us, look at the disc plus block system. There's two objects together. Okay, so disc plus block system. So the two moments, initial moment and the final moment. So clearly there are two distinctions, right, between the different moments. One is before you toss it, and then after you toss it, right? So tell you before you toss it, what is happening is your disc is rolling. The block, you're simply just, before, you can say before it comes together, rotate together. So is going to be the L of the disc. It's rotating before, it's just L. There are two objects plus the L of the block. So this is for the disc plus this of the block. However, the block did not have any initial angular momentum. Okay, the disc is rolling, the block is not. So the initial angular momentum of the entire system is just the disc. So it's just really only to be L. That's it. Okay. To do the angular momentum of the block, remember, the block is a point particle, is not a rigid body. So when we calculate the angular momentum of a block, we do R cross P. Remember, for a point particle, we do R cross P. So we can do this to figure out why it has no initial angular momentum. Initially is R. What is R? R is pointing from the center to where the block is. So eventually the block lands here. So R is this direction. P. Now what is P? P is the momentum of the block. The block is tossed this way, is along the direction of your radius. So you can see that if you look at your velocity this way, sort of the tangential line of this triangle, you might argue the one that's perpendicular down doesn't really need work. You wanted to look at the velocity as horizontal. But if you look at this P, right? is in the same direction of your R. So this cross product is going to be giving you 0. Okay? That's why I said the block did not have an initial angular momentum, because R and P are in the same direction. They're on the same line. So initially it's just L. What about finally? Finally is the disk plus the block will be rotating together with some angular velocity. So I of the total times omega. So that is a final angular momentum of the system. So how does it compare to the initial? Now you will argue that, well, there is no external torque acting upon the system. There is some force between the block and the disk, but block and disk are the entire system. So they're together, right? So that is an internal force. You don't have to consider that at all. Really, all you need to care is the force, disk and block force, the external force. If someone is pushing the disk, if someone is making it spin faster or making it slow down, and that's an external force, and you don't have that. So because you don't have external torque, you can say your L would be a constant. So L initial and L final should be equal. So here, what is the final momentum of your block's disk system? It's still L as equal to before. Okay, so that is the result answer to this question. All right, so that's all we are going to talk about today. Next on Thursday, we'll continue to do more problems using angular conservation of angular momentum to solve more problems. Each time we probably will do a little bit on static equilibrium to look at how do you balance an object. But that's all for today. Okay, if you have questions regarding your midterm, feel free to email me, and I should be uploading an solution to your Blackboard site really soon, maybe later today, or for sure before Thursday. Okay. All right, I'll see you everyone on Thursday. Have a good rest of the day.
Thank you, Professor.
Thank you, Professor. Have a good day.
Have a good one.
Thank you, Professor.
Thank you. Bye-bye.